Hey everyone and welcome. Today we're tackling a Leetcode problem called Rearranging Fruits. It's a fun one that seems a bit tricky at first, but has a really elegant, greedy solution. Let's break it down together. Alright, so here's the setup. We're given two fruit baskets, represented by two lists of numbers. Each number is the cost of a fruit. The goal is to make the baskets equal. We can swap fruits between the baskets, and we want to do this with the minimum possible total cost. If it's impossible, we should return -1. So what does it mean for two baskets to be equal? It doesn't mean the lists have to be identical in their current order. It means that if you were to sort both baskets, they would become exactly the same. In other words, they need to have the same number of each type of fruit. For example, if one basket has 2 apples and a banana, the other must also end up with 2 apples and a banana. Now, how do we fix the baskets? We can swap one fruit from the first basket with one fruit from the second. The interesting part is the cost. The cost of a single swap isn't fixed. It's the cost of the cheaper fruit involved in that specific swap. This is a huge clue that we should probably try to involve cheap fruits in our swaps whenever we can. Okay, before we even start thinking about swapping, we have to ask a critical question. Is a solution even possible? Let's think about the total number of fruits. If we combine both baskets, the total count of each specific fruit, like apples, must be an even number. Why? Because if you have an odd number of total apples, say 3, you can never split them evenly into two baskets. One will always have more than the other. So our very first step should be to check this. If any fruit has an odd total count, we immediately know it's impossible and can return -1. Let's apply this check to the first example. We have basket 1 and basket 2. If we count everything up, we find we have 2 fruits of cost 1, 4 fruits of cost 2, and 2 fruits of cost 4 in total. All these counts, 2, 4, and 2, are even. Great. This tells us a solution is definitely possible. Now we can move on to figuring out the cheapest way to do it. So since we know a solution exists, we also know what the final perfect state of each basket should be. Each basket must end up with exactly half of the total fruits. That means each basket needs one 1 foot, 2 2s, and 1 4. Now we can see the imbalance clearly. Basket 1 has an extra 2 and is missing a 1. Basket 2 is the mirror opposite. It has an extra 1 and is missing a 2. The problem now is just to fix this imbalance. This brings us to the greedy approach. The overall idea is to first count everything up to find out which fruits are in excess and which are needed in each basket. While we're counting, we can do our impossibility check. Then we create lists of all the fruits that need to be moved. Basket 1 has a list of fruits to give away, and so does basket 2. To get the minimum cost, our greedy strategy will be to always make the cheapest possible swaps. Alright, here's the Python code that implements this strategy. It might look like a bit much, but it follows our logic exactly. We'll walk through it section by section, so it's perfectly clear. First, we use Python's counter to find the frequency difference in a really clever way. We create a counter from basket 1, and then we tell it to subtract the counts from basket 2. So if a fruit cost has a positive value in our final frequency map, it means basket 1 has more of them. If it's negative, basket 2 has more. And if it's 0, the counts were already equal. Next, we build a single list of all the fruits that are part of the imbalance. We loop through our frequency map. First, we do our impossibility check. If the count difference is odd, we return -1. Otherwise, we know we need to swap half of the difference. So, we add that fruits cost to our to_swap list that many times. This list now holds every fruit that is in the wrong basket. Finally, we sort this list, which is crucial for the next step. Now, for the most important part of the logic, for any 2 fruits we need to swap, say a 10 and a 12, we have 2 strategies. The to_swap list contains both of these. Because one basket is over by a 10 and another is over by a 12. We can swap them directly. The cost is the minimum of the 2, which is 10. But there's a second sneakier option. What if the cheapest fruit in the entire game costs 1? We could use that cheap fruit as a middleman. We could swap the 10 for a 1, which costs 1, and then swap the 12 for a 1, which also costs 1. The total cost of this indirect route is just 2. We always have to pick the cheaper of these 2 strategies. This is exactly what the final piece of the code does. It finds the absolute cheapest fruit available. Let's call it min overall fruit. It finds the absolute cheapest fruit available. Let's call it min overall fruit. Then it iterates through the first half of our sorted to underscore swap list. For each of these small fruits, it pairs it with a large fruit from the other end of the list and calculates the cost. The cost is the minimum of two things: the cost of the small fruit itself, which represents the direct swap, O2, the min overall fruit, which represents the indirect swap. We add the cheaper of these two options to our total cost, and that's it. So how efficient is this solution? The main performance hit comes from sorting our list of fruits to swap. If n is the total number of fruits, this takes big O of n log n time. In terms of space, we need to store the frequencies and that same swap list, which could take up to big O of n space in the worst case. So to wrap it all up, what are the big ideas here? First, always look for an impossible state, which in this case was an odd total count for any fruit. Second, using a frequency map is a super clean way to find the difference between two collections. The real aha moment is realizing that for any swap, you have a choice, a direct swap or a cheaper indirect one using the global minimum. By sorting the fruits that need to be moved, we can greedily pair them up to find the minimum total cost. And that's a wrap on rearranging fruits. I hope this breakdown was helpful and made the greedy logic clear. If it did, a like or subscribe is always appreciated. Let me know what you think in the comments below. Keep on coding, and I'll see you in the next.